not paused. So the Lunar Environment Monitoring Station is a TRL-6 proposal funded by Dolly that was originally proposed by Mehdi Benna, our principal investigator, and we've been working on it since early 2019. And we have we'll be testing its TRL-6 capabilities end of next year. So to give you an overview, next slide. These are some of the contributors to this presentation. I'm just going to include them up front. So the LEMS concept is a compact, autonomous, and self-sustaining instrument package that will enable long-term in-situ monitoring of the lunar exosphere and seismic activity for a nominal duration of 2 years from its deployment on the surface of the moon. The station's mass spectrometer will collect daily measurements of the exosphere composition. It will also include a seismometer to continuously monitor the moon seismic activities in order to constrain the structure of the lunar interior. This iteration of the package is meant for TRL-6 development, and so we only include those instruments in addition to a retroreflector and a cold trap that is an augmentation for the mass spectrometer. However, the system is being designed to accommodate a variety of future science goals and mission scenarios. So for that reason, we have a high-level mission concept that includes 3 variants of the LEMS station in order to really take advantage of NASA's planned missions for the moon. So LEMS-B variant, which I'll be mostly covering today, has 3 deployment capabilities. The one on the left shows an astronaut. Should we return to the moon? It's within the lifting capability in astronaut. Right now, our CBE is about 35 kilograms. In the next few months, we'll start lightweighting our structure and other systems in order to get that down. In the middle, you see kind of a robotic deployment from the CLIPS lander to the lunar regolith. We also have the capability for remaining on the lander and still achieving our science objectives. Then you have the LEMS-H variant. H stands for Hopper. The concept there is that the LEMS-B payload or LEMS-B package would be augmented with a couple of prop tanks and thrusters to give the LEMS package the capability to jump up to between a couple hundred meters to up to 5 kilometers, so that they could locate themselves in an area of interest that the lander was otherwise not going to, with the potential for several hops given the fuel resources. And then LEMS-L, L stands for lander, is just a larger prop system deployed from a parking orbit where it would come off some type of lander or ferry or shuttle that would get us there. And you can imagine those prop tanks, last time we did that math, was about the size of a beach ball. So next I'll give you an overview of the LEMS-B system. Like I said, it's a Dolly-funded development and advancement of lunar instrumentation, TRL-6 development. It's an augmentation for the commercial lunar payload services, landers, to allow for continuous day and overnight payload operations for 2 years. And I'll go into what about the lunar environment makes that such a challenging thing to achieve for a thermal system. So our payload instrument volume, at least internal to our thermal blankets, that is temperature controlled. Our bounding volume is there, 0.17 by 0.15 by 0.59 meters. And then an overall LEMS-B package volume on the lander is about 0.73 by 0.62 by 0.38 meters. So in terms of capability for instrumentation, the CONOPS allows for transient high power heat loads and a constant or constant low power heat loads. So the differentiating points there, as long as you can keep the instrumentation under 2 watts for continuous power, we should be able to accommodate that. But if you're starting to get above that, like our comm system is, we have to limit their operational window. Otherwise, you risk overheating the internal components. Like I mentioned before, current CD is 35 kilograms. And the current effort for our TRL-6 is baselining a latitude on the lunar surface of 45 degrees, mostly because that's where, based on the ICDs of the current batch of CLIPS landers, that's the first mission they're baselining is in those mid-latitudes. However, we will be expanding our operational capabilities to other latitudes from the equator all the way up to the polar region, with relatively small design deltas, changing the size of radiators, reorienting solar arrays. And then in terms of communication with Earth, we have a monthly high rate comlink that's about 2 hours once a month, and then a weekly low rate comlink for telemetry downlink and station monitoring. So to give you an overview of our development timeline, in early 2019, we had the kickoff for this project. In the top right, you can see the architecture that was proposed for Dolly. If you notice, the lens system kind of has an octagonal shape to it, and that's because the original concept had the blankets being deployed over a large area to try to use the lunar regolith as a thermal mass to mitigate the large temperature swings on the surface, which at the equatorial regions is between minus 160 Celsius and 120 for almost 30 days over that range, so half and half, more or less. You can see, in the middle pictures where we were at SRR in Q3 of 2019, and then how we developed since then to our current thermal model. One of the major changes being, as you'll notice this on the next slide, is that we've kind of moved on from having all of our electronics and science instrumentation inside our structure to a sort of 3-bay system where, in order to reduce the mass of our structure. So to wrap up our timeline, we just finished up blanket emissivity testing of the thermal mock-up you see in the bottom right, provided by Quest Thermal Group and Alan Koplov. We'll be doing heat switch tests on the Sierra Nevada heat switch you're using in this system, hopefully at the end of September, depending on the thermal vacuum chamber schedule at Goddard. We're already working through our subsystem CDRs for our test and integration phase beginning in Q3 of next year, and working all the way through March of 2021, or March of 2022, it's mislabeled. Next slide. So I'll give you an overall architecture overview of the lens system, and then an overview of the thermal control subsystem. So what you're looking at on the right now is the current concept, or at least the mechanical model of it. And you can kind of see the 3-bay design we have going on here. These gray honeycomb panels is our main structure. And the bottom, I've kind of broken it up into a conceptual diagram. So inside our honeycomb structure is where we intend to keep all of our science instrumentation. Right now we have the QMS and the seismometer in there. However, there is room for other instruments that we've been speaking with, one including a micrometeoroid detector, and the other one was a magnetometer. And a mechanical engineer has worked those out to show that they can fit inside. Then on the left here, in this kind of bay, we have the electronics that includes our PSE, CNDH box, which has our hibernation monitoring system, our what we're now calling the processing card, a special services card, and a low voltage power supply. Special services card being the electronics card that is intended to interface with the instrumentation, the science instrumentation on board. And then all the way to the right, we have our big old battery, the 1,000 watt-hour lithium-ion battery. The lunar day-night cycle is, like I mentioned before, 30 days, half of that being nighttime, where we're not taking in any power. So we need quite a large battery to survive that nighttime and our heat losses from there. But a lot of work has been done on the thermal control subsystem in order to reduce our heat leak as much as possible to mitigate the battery mass. Because the commercial lunar payload services the landers have quoted that they're somewhere in between $1.2 million and $1.6 million per kilogram of payload delivered to the lunar surface. So there's almost no amount of money that we could spend in order to reduce the mass of any of this system. And so we're doing a lot of work in that to try to keep our mass down and make our mission competitive for any grant proposals. What else do I want to point out here? The hibernation monitoring system is particularly interesting because it's the way we've broken up our command to data handling between our processing card and hibernation monitoring. Hibernation monitoring was intended to be a low power card that was on continuously to monitor anything that needed to be monitored continuously. That includes the seismometer and all of our temperature telemetry. Whereas the processing card handles transient high power monitoring of the communication system and the QMS. We have 4 solar arrays. The current configuration is sized for 45-degree latitude. The configuration probably looks strange to anyone who works on low Earth orbit satellites, but that's of course because we have the lunar regolith to contend with and maximizing our solar, the amount of solar energy we can absorb. And then of course our communication system, we're using an X-band system with a medium gain antenna for return to Earth and an omni antenna for send. And for that medium gain return, we're getting baseline 256 kilobits per second, and then only 1 kilobit per second uplink because that's something that we don't particularly need a lot of data going towards the spacecraft. Moving on into the thermal control subsystem design, which I'm sure is what everyone's interested in here. The design is largely, as much as possible, passive thermal control. If you count thermostat-controlled heaters as passive, and that's really by design to make this thing as robust as possible and failure-proof as possible. So one of the big flagships of this thing is our high-efficiency IMLI thermal blanket from the Quest Thermal Group. Right now, the current requirement is for an E-star of less than 0.0028. And what's really attractive about those IMLI blankets is that they have the capability for, they get about half the mass for the same amount of blanket area. And the way they do that, the discrete all-temp spacers that allows for, that effectively eliminates the conduction losses you would usually get from using a Dacron mesh or similar. Underneath that big black circle, you've got our OSR radiator plus heat switch from Sierra Nevada Corporation. Good thermal coatings throughout. We have included in the design the capability to include radioisotope heater units. And we've done some of the legwork in talking to the Department of Energy on what the process would be for including those in the design. However, the current TRL 6 effort does not need to use the radioisotope heater units. Those would only be necessary if you have particularly large power, which would necessitate an increase in the radiator size, or you're in a particularly tough thermal environment on the surface of the moon. Everything else, the goal is low thermal conductivity to our external components. The blanket is that orange bit, so our break-off cap we have on the conical standoffs. Our solar arrays are all outside. And then the way we interface the lander, which is in the below the blanket, if you can picture that, is we have a launch lock mechanism that's going to give us the mechanical strength we need for launch, but then the thermal isolation we'll need on the lunar surface. Heaters inside for control. Nominally, they're placed on the electronics panel and the battery panel to maintain those above our minimum temperature limits, which is about -30 Celsius. And then temperature telemetry is your standard run-of-the-mill stuff, thermistors and PRT. Does anyone have questions at this time that I can answer at this point? From here on, I go into the lunar environment a little bit and then on to a bit of the thermal analysis that we've done. No? All right. So moving on to the, here's a summary of our heat loads. You could peruse these at your leisure. You pull the package off the TFAWS website. But the one thing I do want to point out is you'll notice the large disparity between the transponder, SSPA, and LNA, or communications electronics, and everything else we've got inside, where the comm system is going to be generating up to 35 watts, which is huge, or 32 watts, which is a huge amount compared to what we're trying to do with our other electronics, which is keep it down, in the 1 to 2 watt range. And even with the 2 watt stuff like our CNVH, it's on a transient cycle to try to reduce the amount of heat load inside. especially during the day. So the lunar regolith, we have a large, most of the modeling for this, all the modeling for this is done in thermal desktop and Simulate Fluent. And so in order to simulate the lunar regolith, we have a large disk that is 10 meters in radius to get the view factors to the LEMS-B system. And then the model for the temperatures are set for that surface. And that model is taken from the global regolith thermophysical properties of the moon from the Diviner Lunar Radiometry Experiment by Hain et al. You can see on the right comparison between the Hain paper on the top and then what we're predicting for that surface below. You know, the one discrepancy you'll see on this chart is for that extremely low latitude, or high latitude rather, of 90 degrees. We're not currently running any cases for that. That will be fixed when we start, at the point that we start running cases for that. One of the things that we have done a bit of work on and research for is what we expect for our lunar dust contamination. That was taken from a paper, The Effects of Lunar Dust Accumulation on the Performance of Photovoltaic Arrays. Basically, it was a series of photovoltaic arrays on the surface from the Apollo experiments, or rather Apollo missions, and they saw a worst case solar array loss of 1.4% power per year. So you can expect a similar area covering with lunar dust of 1.4% of that area. So we added 50% of margin of that, and then multiplied it by the number of years we're going to be there, so 4.2%. And then at the bottom, you can see the equation that was used to calculate what our true end-of-life absorptivity and emissivity would be for our optical properties. So jumping into the thermal analysis, like I mentioned, we're using thermal desktop. And we cold bias and hot bias the environmental conditions, optical properties, and critical interfaces between the cold and hot cases. You can see what those changes are here in the chart. Solar flux changes, optical properties, all pretty standard stuff. And in the cold survival case, the one thing you'll notice is that we've turned off the instrumentation for, that was non-op. But those really just use the size of the heaters, and the difference between the two is a couple of watts in heater power. So nominally, we're not showing that in this presentation since it is just similar to the cold op case. Progressing. There we go. So cold op case, slide 1 of 2. Got some nice temperature gradient charts on the right showing our peak temperatures and then our minimum temperatures inside. Nominally, the inside of the bus or inside our blanket is expected to operate between -30 and 35 Celsius for the battery. The battery is capable of going up to 50 Celsius, but we need our margin, according to GEV, which is 15 degrees for model predictions. And then because it's somewhat isolated from the battery, the electronics can run hotter. So we're just getting into the chart on the left. I pointed out the two COM links and how they cause a slightly different profile for our temperature plots. It's the monthly COM link, the longer 1-hour ones versus our 10 to 12-minute weekly COM links show a slightly larger response and a slightly longer time to settle back to that nominal curve. I don't know if there's anything else particularly I want to point out. The spikes you're seeing here are daily operations. That's mostly the QMS operations. Next slide. And this is just a second slide showing our external components and what you can expect from those. I don't think there's anything in particularly interesting here that I want to point out. So moving on into our hot case. Although I will point out the radiator on that slide is operating at -20 versus what you'll see for the hot op is about 25 Celsius. And that's mostly due to the difference in heat loads and environmental conditions, but also because the heat switch, because it's operating at a higher temperature, has a larger conductance across it. So nominally you just see higher temperatures here. That QMS RF tank doesn't really have a temperature limit on it. That's according to the science team, so that's nominally fine. And everything else, you see higher temperatures for a hot op case. And then jumping into the external components, you're going to see slightly higher temperatures for some of these external components. Like I pointed out before, that radiator is operating at a much higher temperature. Yeah. So moving on, and then this is a heat flow to give you an idea of what kind of heat flows we're working with. So you'll notice, looking at this chart, our largest heat leak from the inside of the bus to the outside is, at the time this chart was made, was our coaxial cables going to our antennas. Otherwise, it's the heat switch. But all these heat leaks are small. They're less than a watt. But even with that, still, because we're operating for 14.5 days, Earth days, over the lunar night, the lunar eclipse, we do try, every effort needs to be made to mitigate these heat leaks. And so you can kind of see all the way on the right, the total nighttime energy heat leak, with our goal being the battery capacity minus its margin of about 800 watt hours. The time this chart was made, we were sitting around 1,080 watt hours, with most of that energy going towards the coaxial cables. We just wrapped up a trade this week on the coax to switch to a much smaller diameter that the comms engineer was all right with, and that brought us in line with the battery capacity we have available. So to go to conclusion, the LEM spacecraft is a payload platform that would be capable of operating continuously on the lunar surface through daytime and nighttime operations. It can be made available to operate at a wide range of latitudes based on small design tweaks, which, for example, with the radiator size, the solar array angle, and the TCS is reaching analytical maturity in the very near future, with TRL6 testing in late 2021. All right, I'll open up for questions now.
Okay, great. That was very good. Thank you. Let's look online for some questions.
Any questions for Ethan?
I will say the other thing I have available is some of the design trades we did over the process. And if you want to go into those in lieu of questions, I'm happy to do that.
Yeah, I think that'd be great. Thank you, Ethan.
Sure. So include all these are the references, the temperature limit slide. So this is a nice slide showing you the blanket analysis that was done for our initial procurement of the thermal blanket for the mock-up, done by Quest Thermal Group and Alan Koplov, over the kind of ranges. Like I mentioned, that we just pulled that out of the thermal vacuum chamber last week, and we're working on post-processing the data. Nothing seemed too crazy, but the analysis that was conducted, they were getting E-stars well below what what our requirement was. So it's very promising. And the test didn't throw up any particular, the initial results from the test didn't throw up any particular red flags. So that looks like that's coming together well. Though mechanical does have some concerns about geometry bounding, but we're working with Quest on making sure that the blanket is within the dimensions that we expect. It's not necessarily. So one of the things that was done was a trade on the radiator, because part of our hot biasing is to pitch the LEMS model up to 12 degrees so that the radiator can see part of the lunar surface and so it's closer to the sun. That's in accordance with what some of the eclipse landers are expecting for off-nominal pitch they're going to get on the lunar surface. And really, the big result of that trade was you see all of it right. First off, there's a high sensitivity to the, using even one radioisotope heater unit, which is nominally a 0.8 watt plutonium chunk that's included inside the spacecraft, and this just continuously generates 0.8 watts. And so because you're generating 0.8 watts during the nighttime, which is when you want it, also during the daytime, you then have to compensate with more radiator area, which then hurts you during the nighttime. And so it's a bit of a nasty feedback loop. So we've been, we initially for SRR, we were baselining to RHU. And since then, the power numbers have gone up and everything else has gone up. But we've done a lot of work to really eliminate the RHU so that we wouldn't have to deal with the large radiator problem and the other political and regulatory issues that come along with it. But part of this conversation too was also how sensitive we are to the alpha values, the solar absorptivity we were going to get on the on our radiator, on the OSRs we're using on the radiator. And our thermal controls group or optical properties group tends to be very conservative in what they're using. So as a part of conversation with them, we convinced them to bring it down from 0.24 to 0.2. And part of that was really making them comfortable with our dust expectations on the surface. And that has allowed us to significantly reduce the radiator area from that initial number of 661 down to 290, which also helps us reduce our nighttime heat leaks going out of that heat switch in the radiator. So the other thing I could talk about is one of the very first trades we did that I thought was particularly interesting was the deployable blanket trade, where we were trying to incorporate the regolith as a thermal mass into our thermal control subsystem. That's what the DALI proposal was initially proposed on, was using a thermal system like that. And as a part of that trade study, we looked at what we called the umbrella, which is kind of very large. We looked at a sensitivity analysis, increasing size, or really the diameter of it, a couple different shapes, so that's not included here because that didn't really result in anything. And then the box design, which had, it's what I'm showing here, you can see there's a bottom surface to this kind of very large blanket to use the regolith as part of the mass. And then, those are the two big ones. And then what these two confusing tables show you, is the sensitivity analysis of the diameter of those umbrellas to the expected heat leak through that air, the blanket air, through the blanket over the night. And really the result of that, right, so we look on the left, the result of that was that for our cold cases, the heater power at night was, as we got smaller, the as we got smaller, the heat leak really went down. And so, this kind of solid blue line, so that was the one including the without the bottom blanket facing the regolith. So if you're going to go with that design, really you want it to be as close to the blanket to be as close to the spacecraft as possible. But what was also interesting was if you included, if you did not include the bottom blanket, so the solid blue line is including the bottom blanket, and the dashed blue line is without the bottom blanket. Without that bottom blanket, as you increase the diameter of that blanket, you did see a decrease in the required heater power. But if you notice how large it was up to 2 meters, which is incredible. It was 3 times the nominal diameter of our spacecraft at the time. So you had to get very large in order to have an appreciable effect on decreasing that heater power. And the added complexity and mass of a deployable blanket, what the deployment mechanism was going to be, it just wasn't worth it at that point. It's still not worth it now. And so, that's why we are at our current system. And it's more on the lunar regolith model, just some detailed charts on it. And that was it.